Okay. So this was what I told you right now was some more generic arguments to one of the topics I have today. I call to talk aspects of quantum gauge theories, and why I'm, so to say, touching here on several topics in gauge theories you will probably see during my talk. And first of all, I would like to motivate why do we have functional approaches to gauge theories. I will come back to this issue, Coulomb phase, and you see I didn't say confinement or Higgs phase. This is more or less like one phase. I will talk a little bit about what we learned in QCD on propagators and three-point functions. And then I will tell you a little bit about an exploratory calculation of how in such an approach you would see the conformal window, and I tell you some results, and I tell you why these results are not correct. And then I'm going to conclude and present an outlook. Good. So, if you want to study gauge theories, at the very end of the day, you want to connect it to experiment. And what's the most prominent state in QCD? This is the nucleon, proton, and neutrons. And if you have quantum chromodynamics, where would you look for the nucleon? And of course, if you simply think of the propagation of a three-quark bound state, you should find that the corresponding pole. And what do you need to look at? You need to look at the 6-quark green function. How to calculate this piece? Then I guess there is, of course, one, so to say, one direction which is followed by very many people. Yeah, you give up discreteness, you give up continuity of space-time, choose with a lattice a discrete version. Of course, this breaks it down for Fourier invariance and partial-cubic invariance. But okay, at the end of the day, you would like to let the lattice size go to 0 and to find, so to say, the continuum limit again. Then, of course, you can by no means, even on a lattice, calculate the path integrals, so you need some statistical method to find the most important configurations. So it means you use some Monte Carlo algorithms. Is there some kind of pointer here? Okay. And still then, everybody who puts dynamical fermions or dynamical quarks on the lattice knows that this still eats quite some amount of CPU time. Especially because what you need to do, you should let go A to 0, the lattice spacing to 0, the volume to infinity, you need to do extrapolations, and even with the fermions you have, typically you need to do also some extrapolations on fermion losses. Okay, so if you want to do otherwise, what choices do you have to make some statement about quantum field theories in the strong interactive domain? If you want to keep X, if you want to keep here a continuum description, you need to fix a gauge. And in some sense, this immediately will buy you problems with gauge invariance, and I will remark on it. And you get an infinite set of coupled equations. And of course, in order to numerically solve them, you need to chop off the equations at some point, truncate them. And in some, you have some physics guiding principle how to do this. But typically, only the results in the end are going to tell you whether you did do a good job. Yeah? It's not something systematic, it's something which you look upon a posteriori, how you did it. Yeah? And you all know that method 1, if you apply it to QCD, gives you excellent results for hadron properties, it gives you insight into hadron structures, all that stuff. But it has been proven surprisingly hard to learn something about more fundamental aspects. Of course, you can calculate the Wilson loop, confinement is there, but as you probably have seen already in my discussion before, the nature of confinement is still quite elusive. You measure on the lattice a current condensate, but really to find Here the underlying mechanisms for dynamical chiral-symmetry breaking is very hard. Axial anomaly, having different binding numbers on the lattice is a topic in itself. And method 2 is, so to say, not always really fine-tuned to produce numbers. Sometimes it's much more there to produce insight into phenomena. Of course, we also want to obtain numbers. But I guess what happened? Interesting effect. Oh, do I have something heavy to put on there? Mechanical fix for mechanical problem. Hopefully works. Okay. Good. Yeah. We want to understand the confinement and of chemical gluons, quarks, color composites. We want to understand dynamic chiral-symmetry breaking. Yeah? And since the days of Nambu, people are kind of equating the dynamic generation of quark masses with dynamic chiral-symmetry breaking. You have to be very careful. The generation of quark masses is only one consequence of dynamic chiral-symmetry breaking. A very other important consequence of chiral-symmetry breaking is that you generate chirality changing quark-gluon interactions, and I will say something today about this. Yeah? And you also would like to understand the one anomaly topological properties. To this topic I will not say much today, mainly due to time reasons. Yeah? And the methods which are employed are in the recent years very much for the exact normalization group, mostly in the form as equation as derived by Wetterich, as Wetterich equation, but we also quite often use the very old-fashioned Dyson-Schwinger equations, which are by now 60 years old. We mix this with so-called n-particle reducible methods in order to respect some symmetries we would like to keep. And taking this, we put then the correlation functions we calculate as an input into Hadron phenology, and we solve some type of Peters-Salpeter equations for mesons. They can calculate form factors, decays, reactions. You can formulate a covariant Faddeev equation for baryons, calculate nucleon form factors, Compton scattering, meson production, all that stuff. And to say where is the whole thing standing. This functional approach is practically done only in Lambda gauge QCD. I will make immediately remark why. It's in principle an ab initio approach. Perturbation theory is included by construction, and by now we have a very good handle on some elementary Green's functions. So we really work kind of on a solid basis now. Beyond Lambda gauge, things can get very nasty and complicated. And of course, the most severe drawback is we always have these truncations for numerical solutions. So after we have learned for QCD how to do this, this doesn't mean that in another gauge theory the same set of the same idea of truncating the equations will work. Actually, will not. That's one of the lessons we learned. And what's the state of the art for QCD? We can employ a so-called rainbow letter resummation. That's nothing else than some kind of trace-gluon exchange for mesons and baryons in a unified approach. And in QCD, this gives quite good results for a number of mesons and a number of baryons. Generically, if you look then, where's the result good, then you will find out, there where you expect spin-spin interactions in a non-relativistic limit to be not too large, you get with such an approach very good results. If you would look for an axial vector meson, for example, the results are performed not as good. And what's also very important is that you look at a phenomenological kernel. And the one which was most successful in describing pion or nucleon properties was invented by Peter Maris and Peter Tandy some 20 years ago. And a lot of calculations in this business are done with this kind of interactions. There are other interactions doing similarly well, but this is, so to say, what's doable and what can be done by now. If it comes to looking at gauge theories beyond rainbow letter, there are only very few results. They are mostly for mesons. And my PhD student Milan Vjonovic will take part in this school in 2 weeks, and I hope that he will tell you a little bit about his results. And for this reason, I will talk today not about the bound states, but leave this to Milan when he will be here in 2 or 3 weeks. Yeah? So now QCD, as said, in QCD we had some successes, some still very hard problems to solve, but QCD is only one example of a gauge theory, namely of the first one, of this asymptotically free gauge theories. We know by now, or we are pretty convinced by now, that the existence of a UV fixed point can be also not a Gaussian UV fixed point, but a very non-trivial UV fixed point, then you would have an asymptotically safe theory. I guess this is by now also working on here. And I mentioned QED from the aspect of the RG, of the realization group. QED is an RG trivial theory. We know that there is something like a conformal window in between the region, let's say, of an asymptotically free and RG trivial theory. You can distinguish, according to the content you put, a Higgs phase, sometimes have a confining phase, and this is especially here clear. We should not say the Higgs breaks a gauge symmetry, it doesn't. There's Elitzer's theorem telling you a gauge symmetry cannot be broken spontaneously. You break here some certain global symmetry, but of course this is some point I also started to talk before my talk, and this is something we would like to understand. So, and this is what we want to do. Functional approaches are well suited to investigate these related fundamental questions. Then I will talk about the conformal window. If we have something like near conformality, you have definitely a multi-scale problem. Calculating, let's say, for scales up to 6 orders of magnitude on a lattice is a challenge, I assume. This is much less of a problem here. And also what's very nice is that it's very well suited to calculate properties of bound and scattering states, and also to distinguish between bound and scattering states. There have been some recent developments in this direction in lattice calculations, but these are tough and hard calculations, and these approaches are much better suited to this as, for example, to calculate decay width. But as said, today I will not touch so much upon this topic, as Milan will come in a few weeks here. So, so what's the challenge? I said, in QCD, we learned what we should do, at least we are aware of what we should do to get predictive. Now, if you take a new setting means another gauge group, can mean another meta content, can simply mean another representation for the meta content. Whenever you are in a new setting, you really need to solve, again, the system of coupled equations from the very beginning, and need to learn what are important and what are less important ingredients. Good. And why it's so complicated to do this over and over again? First of all, in order to do functional approaches, you need to do non-perturbative renormalization. The advantage is dimensional transmutation is built in, but you need to do this over and over again. In the RG approach, you can say it's already built in, whereas for other kind of NPI methods, it's sometimes very hard. But every time you have then a new setup, you need to worry about how to denormalize. Michele was mentioning today, why don't you use unitary gauge? Unitary gauge would be hell if it comes to denormalization. Then you deal either with integral equations, as in this Dyson-Schwinger equations or MPI methods, and unfortunately they pick up some spurious singularities, which are mostly due to the available numerical methods, and you have to remove this, and they can be there in the ultraviolet and depending on the solution which exists in the infrared. So you have to overcome here a technical problem. Now people have argued, if you use a functional or G, of course it's already already excluded that you pick up such spurious singularities. You have to be very careful that no free lunch theorem hits you here, because then you see these RGs are differential equations containing some integral expressions, and whenever this kind of, and there are something like the differential formulation of these integral equations, so whenever, so to say, the numerical method becomes tough here, you expect the numerical method to become tough here too, and you see this as an extreme stiffness in the corresponding equations. Yeah? So you have here some really hard technical, in this sense we're also not so much different from the lattice community, which also have to solve technical problems. You have to be aware to say, oh, I have now a new set of equations, I learned how to solve the equations. Now this kind of problems might be completely new. Yeah? And then comes the point, why was lambda gauge so successful? Yeah? I will show you today a plot where the kernel, you need to have these tensor decompositions, and the tensor decompositions then lead to kernels in your equations, and today I will show you a plot where the kernel contained approximately 80,000 terms generated by a computer algebra system and directly piped into a GPU code. And now if you go away from a Lorentz invariant gauge, then you can easily add 2 or 3 orders of magnitude here, and the problem really becomes bad. I said already, oh, this is generated by form, and immediately piped into a GPU code. Yeah, this I should have said. Why we are able to do such things, it goes also back to computer algebra packages. One was written by a former PhD student of mine, Dufan, but for mains there was this universal RG machine. Therefore, the numerics, there is some automated version called Crazy DSE, which simply immediately generates your C++ code automatically. And this is for CPUs, and a similar beast for generating GPU-based code is under development in Graz. So, to summarize what I want to say here, yes, every new setting needs a completely new solution of a large system of equations, but by now we also have tools to do this more efficient, but really a number of very hard problems has every time to be solved. Okay. So, this is only to explain where here the man years go into to do this. So let me return now to the issue. Confinement. If you do a lattice calculation, you would say clear and calculate the Wilson loop. And if the Wilson loop shows an area law, then I have confinement. However, if you have dynamical quarks, you never have a strict area law for the Wilson loop. Especially if the quarks become very light, you might even have a hard time to identify a rising part of the potential. And so we follow a somewhat other idea, how we would like to distinguish between confinement and the Higgs phase. So what's alike to the confinement and the Higgs phase is the appearing of a mass gap in the theory. What's alike to confinement and the Coulomb phase is that the global gauge charge is unbroken, whereas in the Higgs it's broken. So can we exploit this simple observation to really find out whether there is whether we can distinguish between this phenomena in a clear way? Of course, there will be some part of our parameter space where confinement and Higgs might be really very hard to distinguish, as I explained before with the water vapor analogy. But in general, you would say you should be very clearly have an operating definition how this works. And this was my student Valentin Marder, Martin Jordan, and myself. And actually, we were building about some quite old picture, namely the one developed by Kubo and Ujima, and they simply looked at QCD in a linear covariant gauge. And you can exploit BRST symmetry to write down the global color charge, which then, if you have no contribution from a massless state, can be written in a very technical way with an anti-ghost operator, a covariant derivative, and the anti-commutator with the BST charge. So this has a formally precise definition, and if you require this to be unbroken, you can derive conditions, and if you non gauge this easier, it was shown by Hugo that if you non gauge the ghost propagator is more singular than a simple pole, you always will have such a very well-defined global color charge. No? If you have this global color charge, then you use a construction known as BRST cohomology to show that all the physical states are BRST singlets. As a BRST transformation is nothing else than a gauge transformation with the ghost field as a parameter, means BRST singlets are necessarily gauge singlets, color singlets. So if you have shown this, you get an astonishing condition from the well-definedness of the global color charge, the infrared behavior of a propagator, and then you get really something which really feels and looks like confinement. All your physical states in the in and out state spaces are color singlets. Huh? One consequence of such a picture is that you get a substantial infrared separation of the gluon propagator, and it's so substantial, this infrared separation, that positivity for transverse, oh sorry, here's a typo, that positivity for transverse gluons is violated. And this has been verified in many calculations on the lattice with functional methods. Whatever you do, as soon as you do some kind of complete calculation, you find that transverse gluons are positivity violating. Why is this interesting? Because it points out positivity violating state is of course an unphysical state. And actually, to this investigation, we were more or less driven by a paper from the 90s who said Kubo-Ujima doesn't work in maximally abelian gauge. And what we learned, so to say, was that the people who have claimed this took Kubo-Ujima very literally. And but you need to go one level deeper, and what's one level deeper? You look at the quantum equation of motion of a gauge boson propagator, and our starting point was that this will discriminate the phases of the gauge theories. And we have BRST, or equivariant BRST symmetry. So BRST symmetry has the property that the BRST charge is nilpotent, and an equivariant BRST symmetry would say that here you get not zero, but you get here only terms which have some certain symmetry. In the case of maximal abelian symmetry, these are U1 or center invariant, here this a kind of Carter subalgebra invariant operators. This is what to understand as an equivariant BRST symmetry. So it's even a weaker requirement than BRST symmetry. And we also needed this for technical reasons, because with help of the BRST charge, we could identify what's an unphysical current. We needed this BRST or equivariant BRST only as a technical tool. And then we looked to a bunch of different gauges and theories, for example, linear covariant abelian U1 with and without Higgs, linear covariant gauge where you could verify the Kubo-Ujima scenario. Here in this linear covariant abelian U1, you see very nicely when you switch on the Higgs, a phase transition from a Coulomb phase to a Higgs phase. We studied so-called cursive Ferrari gauges, which are ghost anti-ghost symmetric. There it goes very similar to the linear covariant gauge. And then we started maximal abelian gauge, and in maximal abelian gauge, it turned out that, so to say, the symmetry breaking or the confining part follows much more the idea of here the abelian subpart forming something like a Higgs background, but actually leading then to a saturation by unphysical currents and to a confining setup. We looked at the Coulomb gauge where the spatial components do exactly what's expected, and then we looked at something which is called Gribov-Zwanziger theory, where you put, so to say, the restriction to the first Gribov horizon into the theory by constraint, And then we realized that the confinement condition is already fulfilled at 3 levels. So if you enforce configurations only existing into the first Kieburg horizon, you get some confinement. So we were able, so to say, in a number of cases, discuss some generic principle. What's the difference between here Higgs and confining phase? And this is really clear, very clearly said. What's the infrared dominant piece? Either you have a massless gauge boson, you have a mass gap in the theory, but in the case of the Higgs, it's a physical current, which then later, as explained in the beginning, leads you to detectable Higgs gauge boson bound state. Or you have infrared separation by an unphysical current, and this is then eliminated from the S matrix. And that's the one piece which is missing.
Sorry, so here we're talking about QCD with fermions, right?
This will all be true if you put your matter into, you can put your scalars, fermions, and of course, this will only be true as certain parts are infrared dominating. But the theory, if you increase the matter content, can change the infrared content, and I will talk about this.
So this is not specific to a given theory. So here I can also imagine it with scalars.
You can, this is not specific to, you can simply take a gauge theory, put a certain matter content, and then the question is, do you have condensation of something, and so on.
So if I had, for example, a conformal phase, what would that mean?
I will come to this. This is the very, because this is of course then the logical question. If you have this idea, how in the hell does the conformal window work? How do you come, so to say, how do you come and really, where does this conformal window sit? What kind of physics do you have there? And this is what I would like to come to. And this was also the origin of our idea that all propagators in the conformal window must be extremely different. But I will come to this. Because this gives you now some unified picture. The only thing is this unphysical part of the current. How is it moved out? How is it kicked out of the world? And there I relate to some earlier work I have done with Natalia. If either in the confinement or the Higgs, you have something like called like an elementary BRST quartet. If you're in the confinement part, you do this business of longitudinal time-like gluon, goes and it goes. If you are in the Higgs sector, you do the same game with the would-be Goldstone boson, the time-like vector boson, and the goes and then it goes. And then by some algebraic relations via the BRST charge and for the Popov conjugation, you can calculate the overlap of these states, and then you calculate an S matrix element, and you put, so to say, 4 Feynman diagrams which contain exactly these 4 states. You add them up. The algebra of this quartet guarantees you that they're out of the S matrix. You can give me an arbitrary Feynman diagram, I draw another 3 Feynman diagrams, which makes it exactly to 0. You follow the pattern algebraically, and the thing has been gone. In the confinement phase, of course, what happens, as the transverse gluon is positivity violating, you can put it, so to say, as a negative norm parent state. You can construct, at least algebraically, what are the other beasts, and you get this cancellation. And this is how gauge-dependent states are removed by this BRST construction out of the S matrix, out of the even-out states. So the whole thing together gives a pretty consistent picture. Good. Now, this is, so to say, how we can understand gauge theories on a non-perturbative level, these aspects of the different phases. But actually, if you want to calculate something, and if you want to verify, is this true that the ghost propagator is infrared enhanced? Does it change if we put in more matter? Then we need to calculate something. And typically what we use is Dyson-Schwinger equations or the Wetterich equation. Yes, for example, the Dyson-Schwinger equation for the ghost propagator, it contains the gluon propagator, the ghost gluon vertex. Or you have such a functional realization group equation. This marks the regulator. It calculates directly the Green's functions, but the scale derivative of the Green's function You see here a little bit more terms, but actually, this is very typical. These renormalization group equations have more terms, but they only have one loop terms. So they have more, but typically less complicated terms. Good. What you can do is you can then apply an asymptotic expansion to all primitively divergent Green's functions. You look at these two sets of equations, and the amazing thing is you have for the same Green's functions two different types of equations. Of course, they need to have the same solution. And this has been exploited by Christian Fischer and Jan Pawlowski to classify all possible solutions. And actually, there is a one parameter family of solutions where the Green's functions need to be infrared trivial. And there is an endpoint, there are two endpoints of this one parameter family. The lower endpoint is, so to say, where the positivity violation of the gluon propagator finishes, and the upper endpoint is one where this infrared triviality turns into power laws, and we get one unique scaling solution. Now, lattice calculations for the gluon propagators show decoupling solutions, and actually until 3 years ago, the usual wisdom was to generate only one solution, and this multitude of solutions of functional equations cannot be reproduced. However, 3 years ago, André Sternbecker and Michael Müller-Preusker show that different restrictions or different elimination of Krivov copies lead to different members of this family of decoupling solutions, and they were speculating that they couldn't get the scaling solution only for the reason of numerical limitations in kicking out Krivov copies in their solutions. It's interesting to know that the scaling solution respects BRST invariance, and the whole discussion, as I had before, stays valid, where the decoupling solution softly break BRST and would need to add modifications to the arguments before in several places. It was suggested by Axel Maas that the infrared behavior might simply depend on a non-perturbative completion of gauge, which then later by this calculation for André Sternbeck have been substantiated. But the most amazing thing, what we found out only last year, is if we go from the space-like side to the time-like side, which also didn't mention is somewhat easier in functional equations than on the lattice. If we do this, we get within numerical accuracy the identical analytical structure for the gluon propagator. And this is kind of amazing that for different functions on the space-like side, you get practically the same analytic structure. I will show you a plot later. Or probably this is how the analytic structure is look like. And it has a little bit of a history because some 10 years ago, on the basis of positivity violation, we were already simply putting the assumption the gluon propagator has a cut along the time-of axis, put a certain parametrization. This was now taken up in a direct calculation by Strauss, Fischer, Kellerman 2 years ago, which directly calculated the analytic properties from a completely reasonably closed set of equations. And what you see here is the real part of p squared, the imaginary part of p squared, and here is a cut, and somewhere in this cut here blown out, the discontinuity, the jump of the imaginary part, becomes extremely large positive, jumps down and becomes negative. In our model here, this was even an infinite jump. But of course, numerically, it can only verify a finite jump. So what we have is that the ghost propagator has a cut and a discontinuity, which is then, so to say, only rising in the infrared, whereas the gluon has a cut and a discontinuity, and this discontinuity becomes extremely large as a typical scale from 600 to 650 MeV. There seems to be some typical scale for the gluon propagator. What we did now, probably I will show this picture first and then I jump back. It's interesting that this is not completely connected, it changes the color. So what we did here is this ghost optimization function, the gluon propagator, they run a coupling calculated from this, and here's the spectral function. And these are power loss, the black curve scaling solution. And what's done here is that we have a numerical solution, a parametrization of the numerical solution, which, so to say, is later on used on the time-like side to calculate analytical properties. And you see what I told here. This is the one endpoint. This is the other endpoint of the solution. And you see that the solutions stop when the gluon propagator doesn't show a maximum anymore. Then this decoupling solution stops. You see that the scaling solution has an infrared constant, coupling constant from the ghost-gluon vertex, and some dropping here. But the more interesting part here is the spectral function. For the decoupling and the scaling solution, the spectral function of the ghost are very much different. But of course, this doesn't tell you anything, but don't couple directly to quarks. Whereas the spectral function for the gluon, for the decoupling and the scaling solution, is within the numerical accuracy identical. And this is something very fantastic. So what's now this scaling solution? The scaling solution simply means that if you have n external ghosts, any ghost legs, n external gluon legs, that the infrared behavior under uniform scaling of all one-particle irreducible vertex functions goes with one common infrared exponent kappa and the number of legs. And in both the scaling and the decoupling solution, you get an infrared divergent ghost propagator such that you have this Kubo-Ojima picture for the scaling solution. You get an infrared suppressed gluon propagator. This relates also to this Gribov-Zwanziger picture of respecting the Gribov quantities. The ghost-gluon vertex is infrared finite, and you get a 3 and 4 gluon vertex, which is infrared divergent, and for the 3-gluon vertex, I will even show a calculation. And one should note that this doesn't only happen in Landau gauge. We found the same classes or families of solution in Coulomb gauge using variational and ERG methods, exact normalization group methods, and in maximally abelian gauge using Dyson-Schwinger equations and also exact normalization group methods. And these exponents of the scaling solution you see very nicely here. So very clearly here this exponent. And you have a scaling relation between the gluon and the ghost propagator. So these exponents are not independent from each other.
Sorry, if I were to calculate, I mean, these are in principle scheme-dependent quantities, right? These are scheme-dependent quantities, all of them.
Yeah, it's Landau gauge, minimum scheme.
So if I were to calculate some physical quantity, like a cross-section, I would calculate, for example, the potential between two heavy quark static sources, where we typically use that as a paradigm for what kind of theory we have. Would that, how would this be related? Because
so for the best we know,
one can always.
For the best we know, and it will show you even a quark condensate, whether you plug, of course you always have to plug in the consistent set, but which one of them you plug in, for example, for the chiral condensate, we see variations in the per mil range, which we would say are purely numerical.
So, sorry, but so these are three different solutions.
These are three different solutions to these functional equations.
Okay. From the same physics.
And as far as we can judge, they lead to the same physics. What we have seen is, this is here from the black and the red curve, I have the corresponding analytic structure. So that's the time-like. Here, these are all space-like momenta. And you see we cover here 8 orders of magnitude. And these are time-like momenta, but now on a linear scale. And you see that whatever these solutions do in the extreme infrared, at this scale has no impact, especially this analytic structure of the gluon propagator is between this beast and this beast identical. And if I calculate a gauge invariant quantity from them, up to numerical accuracy, I don't see any difference.
So this is basically just there. But should I sum all possible? I mean, if I think about the quantum mechanics, if I have several solutions, I typically need to consider the amplitude of the understanding together. It's not just three frequencies.
The whole situation, and this was the interpretation of Axel Mars, looks much more like that lambda gauge is sufficient in the perturbative domain, and we do know already from Gribov that in the non-perturbative domain, lambda gauge is not a unique gauge choice, and this simply seems to be like different residual gauge choices. And he even constructed something.
So they are related by, but this is a guess, they are related by gauge transformation.
The Green's functions are related by transformations which very much looks like Kalatnikov transformations. If you can say the whole set of the observer is related by gauge transformation, that's a hard thing to say.
But in principle, even the gluon mass could be gauge.
There is no mass of a gluon. You have no longitudinal gluon in the gauge. Yeah, now comes something which is very interesting, because we read a lot of papers on gluon mass. Yeah. Actually, what the people don't mean, to be very specific, is they don't mean the gluon is in the massive representation of the Poincare. They also would not deal with the longitudinal gluon. This has to be, so that if they talk about a gluon mass, they mean something very much different as if you would talk about a W mass.
Right.
Okay, first. Second, what they call a gluon mass is exactly for this kind of extreme decoupling solution, the inverse square root of this infrared value. Which, if you would do solid state physics, you would call a debye screening length.
So it's a decoupling, it's a form factor of the gluon to some.
It's you see, the gluon in this decoupling solution seem to have two typical scales, namely one where the maximum sits. By the way, the place where here the maximum sits on the gradient side coincides where here the jump sits on the timeline side. Yeah, this whatever we do, you see this maximum value doesn't move, and this maximum value depends simply to be the important part for this analytic structure. Only if I would now by hand, so to say, let this overshoot and rise, then I would lose positivity of the gluon, very likely gluon confinement, and I would get a completely different analytic structure. And to this I will come back when I discuss the form of conformal. But this multitude of solutions seems to be simply an artifact of either the equations or an artifact of the gauge theory as such. And the point, of course, is don't be very careful if people say, yeah, I go here now and call this a gluon mass. For two reasons. First of all, this has really the meaning of the inverse of this has the meaning of a screening length, as you do in solid state physics, and it's not in this sense a mass. And second, the important scale generated by the gluon propagator doesn't seem to be this value. It seems to be the location of the maximum. This seems to determine the size. You see, we can play a little bit with the system by turning some knobs. And this seems to determine the mass gap, not this value. So the people, to my opinion, were looking always to the wrong quantity, but okay. There are different opinions on this issue, as you can imagine. Three-gluon vertex. Three-gluon vertex, I will mainly talk about this paper with the calculations done mostly by Milan. And we start from this Dyson-Schwinger equation, which is of course unsolvable because it contains a lot of higher order Green's functions. But what we can do is we can do a kernel as a transskeleton expansion, only keep the primitively divergent ones. And then we simply count infrared in the scaling solution, infrared dominance in the ultraviolet dominance in the perturbation theory. And this leads us to the fact that a closed system on equations for the Dyson-Schwinger, for the three-gluon vertex needs to contain at least this element. Now, in the non-perturbative domain, the three-gluon vertex has 14 tensor elements, but only 4 fully transverse ones. Now comes an important benefit of using Landau gauge. There the transverse Green's functions form a system which closes onto each other, so I can neglect the other 10 tensor elements. what we then still do is, in order to get the symmetries right, we apply a cyclic permutation with respect to the external legs to restore Bose symmetry. And what we are aiming for was a hint given on a lattice calculation. If we project this equation back on the tensor, which is there already in free level, is there a zero? Yeah? And actually, if you solve the system, we will see such a zero. And why do we want to know this? First of all, you will see that it's important for the quark-gluon vertex, so every kind of unquenching. I will argue it's important for the conformal window. Milan will probably show you how you use this beast in the bound state equation, and especially in bound state equations for the baryons, it's the leading order term in an irreducible free-body force. Right? So we really want to know how this thing behaves, and that's how the solution looks like of the leading free-level tensor. Yeah? So what's here? The green level here is simply a zero. I have plotted it in a very fancy way, while I have plotted the area sinus hyperbolicus of a 1. Why? Because then for large values it's a logarithmic scale, and for small values it's a linear scale. And you see that here, whereas you start positive for very large values of momenta, of Euclidean momenta, and if you go in, then the contribution of the ghost triangle becomes at some point negative and becomes extremely strongly negative and diverges to the negative region. The other diagrams are not so important, but of course what they do is they shift to the zero. So they are subleading, but exactly their relative size in this region is important to locate the zero. So this is the running coupling as calculated from this three-gluon vertex, and here you see very nicely where the zero is located, and you see again that in the physical region the coupling and scaling solution produce more or less the same result. So we verified that there is a zero in the three-gluon vertex. The position is unfortunately somewhat sensitive to scale fixing, so this is a little bit of a problem. The tensor structures beyond three-level tensors are subleading, so we basically can describe this piece with one tensor structure. And the main point of having here zero is not so much that it turns negative at this point. This is a really extremely low momentum. The point is that if it turns, if I draw such a thing via a symmetrized momentum, let's say P1 squared equals P2 squared equals P3 squared, and here I have the Z1 tilde, which I can choose to 1, the normalization constant. What it does, it shows such a behavior, and the point is that at the scale of lambda ms bar, we have a lambda mom scale, by the way. We have a minimum scheme. At the scale of lambda mom, it's suppressed as compared to its v value. And this is really the decisive observation here. The three-gluon vertex doesn't grow large at hadronic mass scales. I have to say already, for the outlook, if we unquench the system, the quark triangle will be positive, and we of course can expect that at some value of nf, this phenomenon stops and the three-gluon vertex will rise again. But I will come back to this at the very end. Good. Now, if we want to couple quarks, we need the quark propagator and the quark-gluon vertex. Oh, I see I'm already kind of, so chiral symmetry is dynamically or explicitly broken, so we have this representation. The quark-gluon vertex has 12 tensor structures, 8 transverse ones, but interesting is that they always come like chiral symmetry respecting, chiral symmetry violating. So if we now do then solve such a system, and this is motivated from a 3PI action, so we have here the quark propagator equation, and solve here, I have the it's interesting. The projector has not enough resolution to show here the ratio. Okay, this is 1 over 2 NC. So we have these two diagrams. For good reason, we call this non-abelian diagram and this abelian diagram. And merely by color algebra for fundamental quarks, this is much more important by a factor NC squared. So we have the system. This system was very hard to solve. This took us really a long time. But for example, this is what happens if we solve the system. I will explain these numbers later. Yeah, we simply get mass generation. Here is a typical up-down mass of 4 MeV, and then around 1 GeV it rises and separates here at 300 MeV, 320 something MeV. Yeah? And this is how the different tensor structures look like. And you see something interesting. First of all, we have 4 structures, 4 transfer structures which are chiral symmetric. So this is, so to say, in agreement with chiral symmetry. Such things can be also there if chiral symmetry is respected. And you see that we get some significant infrared enhancement from 1 to 2, and also certain not subleading tensor elements are not so small. But this is also true for those which are only there due to dynamical chiral symmetry breaking. So we very clearly see dynamical chiral symmetry breaking in the quark-gluon vertex. These are all type of quark-gluon couplings which do not respect chiral symmetry, which are of the scalar tensor type. Then we have seen something fantastic. We have seen here a 0 in the tree-level tensor structure. And actually, whether here this separates or goes further down, this will, if you put the scaling solution, this we are still investigating, comes the decisive point. How do we know that this comes from the 0, 0 in the three-gluon vertex? So we simply manipulate on the input out three-gluon vertex such that here it's either totally straight or even goes slightly up. And then you see that these functions all react, especially you don't get the 0 crossing here. Also, you don't get the 0 crossing on this here. And I would say, oh, if you change so drastically the quark-gluon vertex, what happens to the quark mass function? So this is the full negative infrared divergence of the three-gluon vertex. This is by straightening the thing by brute force. I simply do this. And the other thing is by even letting it get up a little bit. And you see, for all these things which happen so far in the infrared, this has no influence whatsoever on the generated quark mass. It simply happens too far in the infrared to have any impact, except if you would like to increase the three-gluon vertex even more, then the system starts to collapse, mainly by this chiral broken element rising, 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 and then the system tilts over and doesn't show any solution anymore. So everything is here driven by the three-gluon vertex. And you say, clear, by color algebra, it wins already by 1 order of magnitude. If we put adjoint quarks, then this here would also, this diagram would also have the same prefactor, namely NC half. So it's an interesting test to see what happens if we put adjoint quarks. Of course, with adjoint quarks, you produce much more quark mass, practically double as much, but amazingly, the quark-gluon vertex functions, except that this 0 is gone, doesn't show so strong variations. This is really not as much. I jumped here before a slide which shows something. These are the different contributions to different quantities, like the quark condensate and F pi, or the quark mass, or some average thing of this. If you take out the D-level structure, the whole thing collapses, so this has by definition 100% importance. But if you, for example, take out this G2, then the values here for the condensate change by a factor of 2. So it has some 50% significance. And this G2 here is especially interesting because it's some kind of scalar tensor mixed coupling containing the anomalous chromomagnetic moment of the quark, but also some scalar type quark-gluon coupling, and is chirosymmetry violating. This is chirosymmetry respecting again. But this piece, that this is important, tells you that chirosymmetry is also broken in the way the quark couples to the gluon. Good. So, yeah, now we know the beast, and I told you we also would like to know this for the conformal window. Actually, these results I have shown here these are plots taken from the PhD thesis of Markus Hopfer, and we are going to write the publication right now. But a little bit earlier we made another study about the conformal window, and we want to simply increase the number of light quark flavors or change the representation. Today I will simply talk about increasing the number of light quark flavors, and of course, as Francesco knows best, it's always interesting to investigate a theory with working coupling, but we're also interested in what happens to the anomaly, the confinement, what will be the spectrum of the physical particles, what's the nature of the phase transition, the order, are the gauge invariant order parameters. This is questions which interest us. So, and to make a first point, we did a model calculation. So first of all, we have this set of Dyson-Schwinger equations, quark goes to gluon, and now the quark group gets in fact an F and is feeding back onto the gluon. Okay, and our conjecture when doing this was mainly motivated by another paper which was simply doing some extrapolations of lattice results, and we say this is deadly wrong, because gauge boson and ghost propagators must undergo a significant change. And what we want practically would be a self-consistent calculations of propagators in 3-point functions. We cannot do this yet. So what we did, we wanted to test this conjecture by doing a self-consistent calculations of the propagators by putting a model for the three-gluon vertex. And as soon as we put in the knowledge we have, the result turns out to be insensitive, and we plugged in a pretty simple model for the quark-gluon vertex, and this is of course something we need to improve in future, and you will immediately see why. So the model is such that we have only 3-level tensor structure and multiply here some ghost dressing function and some Fermat, divide by some Fermat renormalization function. Why did we choose this? Because this is used by several people since more than 10 years in different studies, so we have nice comparisons. And second, it's extremely successful if you change from a quenched calculation to the physical number of flavors. So what you see here is this DSE solution quenched and the corresponding lattice results for the quark, for the gluon renormalization functions, and then you switch on 2 light flavors, which with Patrick Baumann was actually something like 20 MeV and some 100 MeV flavor, and this is all the green points. Patrick has here some slight problem with the renormalization, as you see, but except this, the reaction of the system, if you use this vertex, is astonishingly good. So this was another motivation to choose this. Now actually what turns out is that if you look here, for example, at the quark condensate or at the quark mass, that for a small number of flavors you have hardly any dependence, and suddenly it drops, and the critical number of flavors is 4.5. So this was of course a shock, because this cannot be true, and you learned by now why this is the case, because this quark-gluon vertex overestimates the quark group. Here is a picture which shows you that you can also identify with massive quarks the phase transition. Here is a small mass, 10 MeV, a tenth of an MeV, 1 MeV, or 10 MeV, and you very clearly can follow here if you would calculate, so to say, the turning points of this the phase transition. But actually it's the nicest in the chiral limit. we have tested that this doesn't depend on the three-gluon vertex model. It doesn't depend whether we put another function to the leading tensor structure of the quark-gluon vertex. But as soon as we added only one additional tensor structure to test the susceptibility of the system, the number of critical flavors jumped by 1 unit. So this tells us that, so to say, the quark-gluon vertex is a quantity we really need to calculate before we can make a predictive calculation. Nevertheless, what we see here is first of all this coupling we use the decoupling solution, and this is for the quantity calculation for this is more or less the behavior of the ghost-gluon vertex if you wish. This is for 4 flavors, slightly below the phase transition and above the phase transition, the coupling becomes flat. The ghost propagator changes from significantly infrared enhanced to some kind of power law. The same is true for the gluon propagator. This also changes to some kind of power law. Very weakly different from the perturbative behavior. And as said, for 5 flavors, the quark mass is 0, and the quark renormalization function has a deviation of maximally 10% from 1. So what we see there in the conformal window is that the running coupling becomes constant over orders of magnitude. The dynamical quark mass goes away. We have an infrared suppressed quark renormalization function, which means we have an almost trivial quark propagator. Then we see that the infrared enhanced ghost stressing becomes an infrared divergent ghost stressing. The infrared gluon propagator becomes an infrared divergent gluon propagator, and we have to be very careful, because if you would now do an extrapolation, you would conclude exactly the opposite behavior. This, so to say, screening length value m of 0 goes first up before it drops to 0. So with an extrapolation, we would extrapolate exactly the wrong way. We found an F-dependent power loss with very weak powers, and there is no maximum in the gluon propagator, which of course already tells us there is no positivity violation, but we didn't do too many calculations with the piece, because the quantitative predictions would need a calculated quark-gluon vertex. This is what we learned here, but it tells us already that the naive idea that I extrapolate QCD lattice calculations to find out where the conformal window sits is a bad idea. So, good. Why does a conformal window exist? And this is very nice. If you have a very small number of flavors, the anti-screening of gluons dominate at all momentum scales. At some point, the coupling rises, exceeds the critical one, we get dynamic current symmetry breaking, and in the extreme infrared, the quarks decouple. At very large NF, the screening of quarks dominate. We get a QED-like theory, but in between, we have in the UV anti-screening of gluons, which is still larger than the screening of quarks, but the quarks considerably weaken it. So the critical coupling starts to rise, but it never can exceed the critical coupling. The quarks do not decouple in the infrared, and you get no dynamic current symmetry breaking. So what you run into is you run plainly into an exactly balancing situation between the anti-screening of gluons and the screening of quarks, something which dynamically adjusts to each other. And this is the reason for the conformal window. Good. So let me simply summarize what I showed you. In Landau gauge QCD, we have established results for propagators, recent investigations of 3-point functions, and they really justify our basic ideas how a quantum gauge theory should be defined in the non-perturbative domain. If we increase an F, we find an almost trivial quark propagator, but also drastic changes of gauge bosons and ghost propagators, we find a plateau in the coupling over several orders of magnitude. I guess that's probably something I should have really pointed out. From here to here, it's 10 orders of magnitude in p squared. So it really covers a multi-scale problem. And but the point, of course, is this study is flawed in the sense that the quark loop is drastically overestimated, and for this we need to include a quark-gluon vertex self-consistently in such a calculation, and this will then probably allow us to give quantitative results And this we started recently to investigate, but from that end, that my new PhD student is now formulating such a machine to generate GPU code automatically, because this turns out to be a real task. So we started with the technical side. How, if we have such coupled set of equations, we generate a code which is sent on GPUs automatically. But our estimates tell us that in principle it's doable. So hopefully in a year or a little bit more, I can show you something which I would really consider as a prediction from functional methods for the NF critical. And then of course I would also put other fermions like symmetric fermions or joint fermions. So thank you for your attention.
So I think we're a bit out of time, but 5 minutes for questions.
Oh, sorry, it was. Okay. I started a little bit later with the questions.
Then we can ask questions later.
No.
So the nature of the transition from the confining to the conformal, will you be able to study that? Or, I mean, in principle you can, but is it, I mean, so will you be able to ask, for example, what the order of this phase transition is?
The order is
be almost built in by your.
Yeah, you made an important remark. First of all, what we see is a second order phase transition in the chiral limit with the corresponding green field critical exponents. But this is already known from this kind of approaches. If you really want to investigate the universality class, so if it's a second order phase transition, such a truncation finds a second order phase transition. One can phrase this. But within such truncations as we employed it right now, you always find the mean field exponents, because deviations in the universality class come from the vertex function. This would be an even stronger argument. That this was why it was clear to me that with our calculated quark-gluon vertex we would be able to make only one point. Namely how that the propagators above the phase transition will look very much different. Yeah, and then you cannot do a simple extrapolation. So yes, it's within this approach it's a second order phase transition in the full calculation. I'm pretty sure we will verify it's a second order phase transition. To which universality class it belongs, this needs a full self-consistent solution of the three-point function. The behavior of the three-point function is crucial for identifying the universality class. Yeah. But then of course we can do it pretty reliable. Yeah. The only thing it's a very large self-consistent calculation.
Yes.
I mean, it is guessed that actually you see there how is the phase transition means infinite order loops. It is guessed. So or actually I say guessed because first order. So what I don't understand is would you trust the order comes from the computation, or it's just a model dependent computation and therefore you can't really
at the moment I would refrain from telling, but in case it's such an infinite order Miransky type phase transition, then you also know how to identify this.
Right.
And actually in QED3 we found such a thing.
Yeah. So let me just rephrase the question. Assume that you were able to calculate the three-gluon vertex.
The quark-gluon.
Would that be enough to be sure of the order of the phase transition, whatever comes out of this computation, or still would be model computation that you will say like, okay, it's an interesting result, but I need to have a lot of this to tell me what it is.
No. If the quark-gluon vertex, if it's really reliably calculated, then you can absolutely tell what's the order of the phase transition and what's the universality class of the phase transition. And I guess this is really a highly interesting example how lattice calculations and these methods can work together to really pin down a result. Each of them would not do 100%. Why? There's Jonas Colorad on the Sternbeck doing a calculation of the quark-gluon vertex, also for dynamical setup, which gives us the confidence that the truncation we're going. I'm absolutely confident that the truncation we've chosen will produce the correct quark-gluon vertex. But we will cross-check this against lattice calculations. And then we can be really sure, okay, we've got all essential information from the beast, and if we have this...
But the lattice, technically speaking, cannot have a continuum number of flavors, right? So they will never be able to tell you there is actually a walking transition because it's
Yeah.
an F plus 1
Yeah, but-
plus
but-
1,
yeah, but-
technically speaking.
But you see, you know,
So in a way they can never distinguish between jumping and walking.
yeah, but look, that's exactly the interesting merger of your two techniques. Because we know from lower dimensional field theories, from condensed matter systems, from the corresponding Cauchy studies, that at the 3-point function, so to say, if you include the 3-point function correctly, you identify the universality class, also the order, if it's second order, the universality class, and so on correctly. Now, if we have here a complete truncation, so we can simply definitely tell all these things. Now you can always, of course, play devil's advocate and say, yeah, look, you did not so much effort, but I tell you, these Green's functions with 17 legs, this is going to change again. You can never logically dispute such an argument, but you can say, okay, for all kinematical settings which are accessible to lattice calculations, for all numbers of flavors which are accessible to lattice calculations, our quark-gluon vertex is verified. It's the same. So that our truncation is complete, we can verify by cross-check with lattice calculations which are right now under the way. And then, of course, you can be extremely sure that whatever this approach gives you is the right answer. And then you do something, the lattice would need billions of CPU hours. You really finally scan everything. You have integer as a non-integer number of flavors in very small steps. You expect a critical exponent. Even by bifurcation analysis, you can go there, take the equations, do a bifurcation analysis. You have all the tool set. You see, you have then all the tool set analytically. This type of continuum equations give you.
I mean, the Taoist transist is just, as you know, the demonstration there is another ultraviolet fixed point that collides with the infrared one. So it's enough, it's not even needed to actually study exactly that. But it would be just sufficient to determine that there is another ultraviolet fixed point away from infrared for an F less than the critical value. That's the principle. We don't need to do that because to see whether there is another fixed point in the field away from the, I mean, for an F large enough. But and then I have another question. I mean, you said you were just already studying what happened with the joint map.
Yeah.
So but I didn't understand. It was actually because when you had a joint matter, there could be also white fermions, doesn't have to be here. So many did you put? At one point, you said there was also studying. You were also studying the gluon vertex in the case of a joint matter.
For joint matter, we were putting, because we were very interested in between whether there's only a color suppression of one of the two diagrams to take into account, or whether there's also dynamical suppression. And our answer is there's also dynamical suppression.
Because in that case, I can calculate with the 100 exact calculation the condensate by the shifting trick. So the question is that at one to that. If that is typical triple flames, that it comes from. We can prove that it comes from the instantons, correct? The condensate of the fermion. So I'm just trying to say what is a relation between the two.
No, this I didn't tell because I didn't have any time.
Yeah.
We actually do know how for the scaling type of solution we get the topological sustainability. It's completely determined by the infrared divergence of the curve. And the point, of course, is we can really calculate the topological sustainability for Green's functions. This contains infinitely many diagrams. You take the leading one, you get 80% of the typical value you use for phenomenology, you get only the prime mass. So things doesn't look too bad.
No, I was saying that from the case of one while a joint fermion in.
We did put a Dirac fermion. For the while fermion, we would need to put another tensor structure of the quark-gluon vertex. Yeah, but this is not, by the way, you're not the first one pushing me to this direction, say, hey, the analytical results.
There are exact results there, so it makes sense to compare it.
Yeah, but you should not underestimate changing tensor structures needs a full run from the very beginning.
But that's why I asked me when you say a joint, but it was Dirac or it was.
Yeah, but there's a bunch of interesting things to do, and if you have the feeling you would like to join, you have to do that.
The question is, I know the result in that case, I don't need to calculate it again. So in that case, I wouldn't do a computation with you, but I would test if an approach with an exact result, so just to be able to see whether that it actually gives the same result. Because you were mentioning the adjoint, I thought you were already looked at it.
No, because for the while you have a tensor structure, and this makes a rerun of the full program.
So if there's no more question, let's thanks.